Hi, I'm Zach, and this is my fourth year MSci research project, Fantasia Synthesizing Recursive Functions Without Trace Complete Examples. Program synthesizers such as Fantasia aim to automatically write a program given some specification, in this case a set of input-output examples. Existing techniques often struggle with recursive functions. Typically, they force the user to specify very specific, unnatural examples in order to work. Fantasia is our solution to this problem and more. So why is this a problem? Well, it comes down to this. Suppose we're synthesizing a function to duplicate each item in a list. The synthesizer has gotten this far, and at this point we just need to make a recursive call on x's prime. The problem is, in order to do this, we'd need to know how stutter would behave on x's prime. Our examples don't tell us this, and so synthesis fails. We really want the synthesizer to do this for us automatically. And that's exactly what Fantasia does. So if the problem is not knowing the result of the recursive function call, why not just run with this and keep it unevaluated until we do? So to do this, we introduce recursive calls as early as we can. Initially, the recursive calls will be thunks, in other words, unevaluated pieces of code. And as we synthesize the function further and further, we can gradually evaluate this thunk. Eventually, we'll hopefully reach a point where the thunk looks a lot like our desired output, and at this point we can unify the two. So let's go through the previous example of stutter from the start with our new techniques. We start with a case split once again, and we filled in the trivial case of the empty list already. We now have to synthesize this purple box. So we introduce a recursive call immediately on x's prime. The result of this call is handed to an auxiliary function f. Its fourth argument is the new thunk shown using angle brackets. The thunk can be evaluated further by definition of stutter, and once more again. And we can proceed normally for now, seeing as the example's output is some application of the cons operator. The head is trivial, so for now we skip the details. For the tail h, it's not so simple. Note we've evaluated the thunk one step further now using the definition of h. Again, we introduce a cons operator and fill in the trivial head. But for the tail, we can evaluate the thunk a little further once again. It now looks a lot like the output we want. In fact, if I applied to these arguments would return the empty list, it would be identical. So we assume that it is, and this removes the thunk altogether and leaves us with an additional unifying example. Trivially, we just return the value of the recursive call r at this point, and we're done. This function is exactly what we expected, but we only need to provide two examples for it. To conclude, the techniques we've presented here let us synthesize recursive functions with fewer examples than we would have needed otherwise, and not only fewer but also less convoluted examples. It's tricky for a user to provide trace-complete examples without knowing the definition beforehand. We've implemented these techniques in Fantasia, an extension of the Fugue programming language, using Haskell. And combining Fantasia's speed and ease of use with Fugue's holes and powerful type system gives us a really powerful paradigm for interacting with the compiler, as if having a conversation with it. In the end, this makes programming easier and more fun. Thanks for listening.